In this video, 3 types of tissues will be heated in a microwave to stimulate the heating process of an ablation probe. The temperature will be monitored by Physio's temperature fiber optic sensors. Ablation probes usually generate constant power of radio frequency waves which lead to non-uniform heating of tissues. This effect will be enhanced if different types of tissues are targeted by the ablation because of their difference of conductivity. Penetration variation of radio frequency wave also contributes to non-uniform heating. This is what we will be demonstrating today. In fact, if excessive power is generated, higher temperatures can be reached and lead to internal lesions. Temperature monitoring will ensure that all tissues reach the adequate temperature for ablation. For this experiment, a multi-point temperature sensor will monitor the temperature at 4 different positions. These sensors are all connected to the SPCHR module and to the ablation software, where we will see real-time graphing. These sensors ranges from 10 degrees Celsius to 90 degrees Celsius, and their accuracy can exceed 0.5 degrees Celsius. We made sure that the size of the sample is identical for each tissue. First, the multi-point temperature sensor is placed in the tissue with the needle to get an overview of the temperature at 4 different positions. The temperature is measured each 20 millimeters to cover the entire tissue sample as illustrated here. We can now follow the muscle's temperature with the evolution software. The blue curves represent the edges of the tissue. We can see that they heat faster than the yellow and orange curves that represent the center of the tissue. The muscle reaches at most 40 degrees Celsius. Let's continue with fat tissue. The multi-point sensor is placed exactly as it was with the muscle sample. The microwave is set at power level 3 for 20 seconds. For liver tissue, we place the sample with the multi-point temperature sensor in the microwave at power level 3 again for 20 seconds. Such as we observed for the muscle, the blue curves are increasing faster than the 2 others. The edges of the liver sample heat faster than the center. The liver reaches at most 28 degrees Celsius. Let's now place the multi-point sensor in this tissue to cross fat and muscle tissue. It will give us an overview of the temperature at different depths. The 4th channel is directly in the fat, while the 3rd channel is in the muscle. We can observe that the muscle heats faster than the fat. When fat reaches its melting point around 50 degrees Celsius, we can observe drops of temperature due to the change of phase. Because the tissue's heating rate is proportional to its conductivity, we can expect that muscle will heat faster than liver and fat. We can observe on this graphic that the muscle's temperature increased in average by 15.1 degree, the fat by 6.7, and the liver by 12.1. As we expected, due to its low conductivity, fat heats slower than liver and muscle, who both have closer heating rates and conductivity. As we observed with the real-time graphing, the edges of the tissue heated faster than the center for the liver and muscle. For the fat, the center heated faster than its edges. This illustrates the importance of temperature monitoring because of the different heating rates due to tissue types and penetration depth. The small probe size makes Physio's temperature sensor an ideal monitoring solution for catheter ablation. It will help prevent tissue charring, steam pop, and internal lesions. For more information on our product and application, please contact us and visit us on our website.